Hey everybody! In this video, we are going to take a Unit 8 test based on the topic of solutions. All of these questions will come from the Chemistry Olympiad, except for 2 of them. Without further ado, let's begin. Number 1. Which combination of dilute aqueous reagents will not produce a precipitate? So for this problem, we simply have to do double displacement for all the reactions. So here we will have AgCl and HNO3. Will this produce a precipitate? Well, we know that silver chloride will be a solid because chlorides are insoluble with silver cations. So A is out. Now what about B? NaOH and HClO4. If you switch those up, you get NaClO4 and H2O. Will this have any precipitates? Well, if you remember, perchlorates are usually soluble and there are usually no exceptions. So in this case, sodium perchlorate will be soluble, and in addition, the sodium is always soluble, and water, well, water is just water, it's part of the solvent. So I think the answer for this question will be B. But let's take a look at the other answer choices. C, BaBr2 and Na2SO4. So you will get BaSO4 and 2NaBr. Now this will be soluble, but I think this one will form a precipitate because sulfates form precipitates with barium. Now what about this? I think this will be Ki and ZnOH2. Now if you want to balance this, we could put a 2 here, and that would just put a 2 there, and it would all work out. So potassium iodide is going to be soluble, but zinc hydroxide is going to be insoluble, since most hydroxides are insoluble except for the exceptions, which include the alkali metal cations NH4+, and the 3 or 4 alkaline earth metal cations. So therefore, C and D are out, and B is our answer. Number 2. A solution of a flame of which metal produces a bright red color in a flame test. So the answer is lithium, because potassium produces a pink flame, copper is a green flame, and sodium is a yellow flame. So these 3 are out. Now let's look at number 3. What is the concentration of chloride ions in a solution formed by mixing 150 mL of a 1.50 molar sodium chloride solution with 250 mL of a 0.750 molar magnesium chloride solution? So the concentration of chloride ions will definitely come from the Cl's in either of these. So we need to figure out how to do this problem. We need to figure out the concentration of chloride ions. Now, how do we do that? Well, we know that the concentration of chloride ions is equal to the moles of chloride ions over the liters of solution. So let's first find the liters of solution. We know that we are mixing 150 mL of the first solution and 250 mL of the second solution. So this must mean that when you add these 2 volumes together, then that means that the volume of our solution is going to be 0.400 liters, because 150 plus 250 is 400 mL, or 0.400 liters of solution. Since volumes, in this case, since you're mixing 2 solutions that are made of water together, these 2 will have additive volumes. So let's now figure out how this works by perhaps drawing a picture. So we have this solution that's 0.150 liters, and it's 1.50 molar of sodium chloride. Now the other solution has 250 mL or 0.250 liters of a 0.750 molar of MgCl2. So when you add these two up, as you can see, the volumes are additive, and if you add 0.15 liters and 0.25 liters, you will get, of course, 0.400 liters. But now we have a bunch of ions, and we need to find the moles of chloride. So how do we do that? Well, we know that moles is equal to molarity times volume. Now, how do we use this? Well, the moles of NaCl is equal to the molarity of NaCl, which is 1.50, times the volume, which is 0.150. And doing the math, we get that 1.5 times 0.15 is going to be equal to 0.225 moles of sodium chloride. Now, how many moles of chloride are there? Well, there's 1 chloride per sodium chloride, so there are actually 0.225 moles of chloride. So we can draw this in our picture. So 0.225 moles of Cl-. Now we need to find the amount of chloride ions in this solution. So we have to do the math again. 0.750 molar times 0.250 liters is equal to, let's see, I get 0.1875 moles of MgCl2, and for every mole of MgCl2 we have 2 moles of Cl-. So this means that there are twice as many moles of Cl-. So multiply this by 2, we get 0.375 moles of Cl-, and we could add that to our picture. So 0.375 moles of Cl-. Now we have the moles of Cl-, and we have the total volume of the solution. We can find the molarity of Cl-. So the moles of Cl- will be 0.225 plus 0.375, and that actually gets us 0.600 moles of Cl- present when the two solutions are mixed, and we divide that by the volume of the solution when you combine the two solutions, and that's 0.4 liters. And doing the math, we get that the molarity of the solution is 1.5 molar for Cl-. So this is our answer, and it seems like our answer is C. Number 4, which of the following is a non-electrolyte in aqueous solution? So the non-electrolytes are the ones that are not salts or acids or bases. This is an acid, so it's out, and that's actually a strong electrolyte because H2SO4 is a strong acid. Now this is a salt, which is a strong electrolyte, that's out. This is also a salt, which is a strong electrolyte, so that's out. Now this is actually a molecular compound, so it kind of looks like this. So it has 2 H's and it has a double bonded O there. And that is not a salt, that is a molecular compound, so D is our answer. And if you remember, an electrolyte is something that produces ions when dissolved. All 3 of these produce ions except for this one, which is a molecular compound. So that's why D is our answer. Let's take a look at number 5. An aqueous solution of potassium sulfate has a freezing point of negative 2.24 degrees Celsius. What is its molality? So if we remember, freezing point depression is going to be equal to, let me see, TF is equal to KF times the molality of the particles. So you know that the molality of the particles is equal to the molality of the salt in question, or whatever compound you have, times the I value of the compound. So essentially we're trying to calculate the molality of the compound and not the molality of the particles, so watch out for that. So we need to know the freezing point of water, and the freezing point of water is 0.0 degrees Celsius, and that means that this freezing point depression that we have will go from 0 to negative 2.24 degrees Celsius, which means that delta TF will be negative 2.24, or actually no, it'll just be a positive because we actually subtract this number from that. So this number is equal to KF 1.86 times the molality of the particles, and doing the math, 2.24 divided by 1.86 will give us 1.20 is equal to the molality of the particles, but we know that the molality of the particles, 1.20, is equal to the molality of the potassium sulfate times the I value of it. Now we assume that everything is ideal, so the ideal I value of potassium sulfate will be actually 3. So 1.20 equals the molality of K2SO4 times 3. And we get that the molality of K2SO4, so let me write that, is equal to about 0.400 molality. So the answer that is closest is A, and it's off by 0.001 due to rounding. Now, number 6. Barium chloride reacts with sodium sulfate according to the following reaction. So they did all the balancing for us, that's great. A student mixes a solution containing 10 grams of barium chloride, and they give us the molar mass, with a solution containing 10 grams of sodium sulfate, and obtains 12 grams of barium sulfate, and they want the percent yield of this reaction. So we have to convert everything to moles before we start. So 10 grams of barium chloride, so 10 divided by 208.2 will actually give us 0.0480 moles of barium chloride. And how many moles of sodium sulfate? Well, 10 divided by 142.1 will give us 0.0704 moles of sodium sulfate. So to find the limiting reactant, we actually have to find which one of these will produce the lesser of the product, since the one that produces less product will be the limiting reactant. So we have to figure out how many moles of barium sulfate each of these can produce. So since everything here from BaCl2 to BaSO4 is a 1-to-1 ratio, this means that 0.0480 moles of barium chloride will produce 0.0480 moles of barium sulfate. Now, the equation also states that for every 1 mole of sodium sulfate, we produce 1 mole of barium sulfate. So that means that we can produce 0.0704 moles of barium sulfate from the sodium sulfate. Now, which one's our limiting reactant? Well, it's going to be barium chloride because it produces less of the product. So because of this, this will actually be the amount of product that we are expected to get. And yeah, so we are expected to get 0.0480 moles of barium sulfate. And let's do the math. 0.0480 times the molar mass of barium sulfate, which is 233.2. And we get that the mass of barium sulfate that we are supposed to get, given the limiting reactant, is going to be 11.19 grams, and I should make that 11.2 to be consistent with sig figs. And of course, because barium chloride was our limiting reactant, then our sodium sulfate will be in excess after the reaction occurs. So we are expected to get 11.2 grams. What did they say in the problem? They said that they got 12 grams of it. Wow. They got more than what is actually predicted by the reaction, assuming 100% completion. Now that's a little bit odd. So let's read our responses. These three are wrong, since the percent yield is actually the amount that we actually get, so 12.0 grams, over what is predicted to be produced, which is 11.2 grams. And this predicted number is the maximum yield assuming 100% completion. So how can we be producing more in real life than what is chemically allowed according to our calculations? So this has a percent yield that is greater than 100%, and this usually tells you that the measurement of either of these numbers might be wrong, but we know that this number is right. But this number is wrong because, well, let's find out. D says the isolated barium sulfate is most likely wet, since the yield would otherwise be greater than 100%. Now, I think this is right because if the salt was wet, then that means that it would be heavier than normal, and if it's heavier than normal, that means that it's not an accurate representation of how much barium sulfate that we actually have. Instead, this might be barium sulfate with a bunch of water, and if it's contaminated with water, it will be heavier than what it's supposed to be, and because of that, it might give you a percent yield that is greater than 100, so this is probably happening. So let's move on to the next question. Which aqueous solution has the highest boiling point? So all of these are one molality, as you see. So I think we know that the boiling point elevation is going to be delta TB equals KB times the molality of the particles. And we could substitute the molality of the particles with the molality of the salt times the I value. So, I mean, it's not always a salt. We can just call this molality of the substance times its I value. So we know that KB will be constant, and we know that the molality of the substance will be constant. Now, what will cause this to be greater or less? It will actually be the I value. If this is higher, then this will be higher. And the one with the highest boiling point will have the greatest change in boiling point elevation. So we need to find the I value of these substances and see which one is the highest. So acetic acid is a weak acid because it does not ionize completely into H+, and CH3COO- or the acetate anion. So because of this, the I value will be between 1 and 2. Now what about sulfuric acid? Well, H2SO4 is guaranteed to split into H+ and HSO4-. So that's guaranteed 2 particles. Now this is a weak acid, so it will not split completely or ionize completely, so we might have some H+ and SO4 2-, but this is not guaranteed, and because of this, our I value for sulfuric acid will be between 2 and 3. Now phosphoric acid is a weak acid, so not all of the H3PO4 will split into H+ and H2PO4-, and because of that, the I value will be between 1 and 2. Now what about glucose? Glucose has an I value of 1 because it is a sugar and the OS is a dead giveaway. So because of this, the one with the highest I value is sulfuric acid, so 7 will be B. Let's look at number 8. A white ionic solid is dissolved in water. Addition of a solution of sodium chloride, NaCl, to the solution results in a white precipitate. What was the cation in the original ionic solid? So it is saying that sodium chloride is dissolved and there's a white ionic solid with an unknown formula unit, and it says that a precipitate forms. So let's think about this. Sodium and the cation here will never form a precipitate because sodium is highly soluble. So this means that the precipitate must form between the Cl and this mysterious cation. So this cation has to precipitate with chloride. Now which one of these do that? Well, I think silver will precipitate with chloride to form silver chloride, an insoluble salt. So C is our answer. Now let's do number 9. Which solute dissolved in 1 kilogram of water will give the solution with the highest boiling point? So this one is going to be quite a challenge, honestly, but I think we could do this. So let me circle our answer there as C. And let's think about this. So we know that molality is going to be equal to the moles of solute over the kilograms of water, and we know that there's 1 kilogram of water, so we could just write 1 kilogram of water here. And we know that this is equal to the molality of the substance, but we want the molality of the particles since we're dealing with boiling point. So the molality of the particles will be equal to the molality of the substance, which is right there, times the I value. So we have many things to consider. We need to find the moles of each of these substances, and we need to find their I values. So what I think we can do is that we can kind of determine which ones have an I value of 1 and which ones don't. So the ones that have acid tell us that it's going to be a strong acid or a weak acid. And let me tell you, if it's not on the strong acid list, it's usually a weak acid. So this is a weak acid, so it has an I value of between 1 and 2. Now the rest of these will have an I value of 1 because they don't have an acid in their name, and this implies that they are molecular substances. So the next thing I did was I found the molar masses for each of these substances, and after that I converted grams to moles for each of these substances. And since moles divided by 1 kilogram of H2O is just the same number, then I knew that the moles of the substance would equal the molality since we had 1 kilogram of water. So for A, B, C, and D, the molalities of the substances were these. Now, I want the molalities of the particles, so I have to multiply by the I values. And notice how most of them were 1 except for B. Now, B is a special case because from a video about ionization that I made for weak acids, we learned that weak acids typically don't ionize completely. They maybe ionize about 5% of the time. So because of this, I assumed that the I value would be closer to 1 than it would be to 2, since not most of them ionize, only a few of them ionize, and because of that, the I value is closer to 1 than 2, so I guessed that the I value was about 1.1, which is close to 1, and doing the math, I get that the molalities of the particles are here, and the one with the highest molality of particles will be the one that will stimulate the highest boiling point change, and thus the answer I found for this question was D, because this is the highest molality out of all of them, and thus D is our answer. Now let's take a look at number 10. The constant for carbon dioxide in Henry's law is 3.4 times 10 to the negative second molar per atm at 298 Kelvin. What is the concentration of carbon dioxide in a soda if a company pumps 62.39 pounds per square inch of carbon dioxide into the soda can, and I'm assuming it's at 298 Kelvin since there's no other indication of temperature? Assume that the solution is saturated. Okay, so for this question, I need to convert PSI, pounds per square inch, into ATMs. So 62.39 PSI times 1 PSI over 0.068046 ATMs. And we get that the pressure in ATMs instead of PSI turns out to be 62.39 times 0.068046. We get 4.245 ATMs. Now we can use Henry's law. C of the gas is equal to K times the partial pressure of the gas. And we know that K is equal to 3.4 times 10 to the negative 2 molar per ATM times the partial pressure of the gas, which is 4.245 ATM. And the ATMs cancel out, and we're left with, let's see, 3.4 times 10 to the negative 2 times 4.245, and we get that the concentration of carbon dioxide in the water at 4.245 atmospheres is going to be 0.144, well actually it's going to have 2 sig figs, so 0.14 molar, and that turns out to be C. Now this one is a free response question, so we have to answer the questions using principles of molecular structure and IMFs. So it says compound 1 and 2 in the data table above have the same empirical formula, but they have different physical properties. So here are their empirical formulas, and we find that one of them is slightly soluble in water, while the other one is soluble in water, and we note the boiling point differences. So the first question says, complete the Lewis structure, so let's do that. So let's draw it a little bigger so that I can actually see it. And I'm going to put single bonds between the C's and H's because H only needs one single bond. And let's see, I think it looks like that. And the lone pairs are here. And let's see, I think there's actually a single bond between the C's. And this would be the Lewis structure for A1. Now what's A2? It says draw the Lewis structure of the structural isomer of the compound represented in box X. So isomers have the same molecular formula, but they might have a different structure in terms of bonding. So how about this? Instead of putting CCO, let's try COC. That would create an isomer. So let me actually clear the ink since you know the answer for AI. So let's put COC instead. And let's connect the H's as always. And let's connect the H's like that. And let's connect the O's like that and put two lone pairs on there. Now, does this mean C2H6O? Well, there are two C's, there are 6 H's, and there is one O. So I think this would be a good structural isomer for the compound. So this would answer II. Now, what does B say? On the basis of the complete Lewis dot diagrams you drew in part A and the information in the data table above, identify which compound, 1 or 2, has the structure represented in box X. Justify your answer in terms of IMFs. Okay, so below we have X and Y as we drew before, and we have to see which one of these compounds represents the Lewis structure in box X. So how does this work? Well, let's think about this. It says that compound 1 has a lower boiling point than compound 2. So how do we compare these boiling points based on the Lewis structures? Well, I think that this one will have the higher boiling point because it has LDF, it has dipole-dipole forces, and you want to write these out in complete words when you write this as a free response question, because not everyone knows what DDF means. And this also has some H bonding involved. Now, what about this one? This one definitely has LDF and dipole-dipole forces, since if you think about it, this molecule is actually bent, and if we draw it like this, and let's just make it bent so that you can clearly see that it is bent based on the electron geometry, then you notice how the bond dipoles are like that and the net dipole goes up, and thus this has dipole-dipole forces. But since molecule X has hydrogen bonding as well as dipole-dipole forces because of this bond dipole, then that means that compound X will have the higher boiling point. So does compound 1 or 2 have a higher boiling point? Well, compound 2 has the higher boiling point, and we said that compound X has a higher boiling point. So this means that compound 2 must represent X. So I will show you the answers later, but let's move on. So C states that dichloromethane has a greater solubility in water than carbon tetrachloride has. Account for this observation in terms of the intermolecular forces between each of the solutes and water. Now, if we remember, like dissolves like, so things with more similar intermolecular forces are more likely to dissolve one another. And this is because the IMFs formed between like substances typically release enough energy to make up the lost energy spent breaking the other IMFs. Meanwhile, for unlike substances, what typically happens is that the IMFs formed are weaker than the IMFs that are broken, and because of that, unlike substances typically don't dissolve one another. So, in this question, it says that dichloromethane, which looks like it's polar since it has these bond dipoles here, and it says that this is more soluble in water than carbon tetrachloride, which seems to be nonpolar because all the bond dipoles seem to cancel out. So we can say that CCl4 has only LDF, while dichloromethane has LDF and dipole-dipole forces. And this would explain why the dichloromethane is more soluble in water than carbon tetrachloride, because for carbon tetrachloride, it can only form LDFs between itself and water, and these LDFs that form between CCl4 and H2O are weaker than the hydrogen bonds that are broken by the water in the first place. And because it is not thermodynamically favorable, that means that the mixing of carbon tetrachloride and water will not happen since it is overall endothermic. And because of that, CCl4 will not dissolve very well in water. Now what about dichloromethane? Now dichloromethane can form dipole-dipole forces with water molecules. So let me just put the link there. And these two can form dipole-dipole forces. And these dipole-dipole forces between water and dichloromethane are strong enough sometimes to release enough energy to counteract the loss of energy absorbed when breaking the hydrogen bonds between the water. And because these dipole-dipole forces that form between this and water are stronger, that means that it is more likely to dissolve in water, and thus it has a higher solubility. So I'm not going to write that, but we will look at the explanations later. Let's take a look at D. In terms of intermolecular forces, explain why DCM, dichloromethane, has a higher vapor pressure than carbon tetrachloride. Well, we know that dichloromethane has both dipole-dipole forces and LDF, while carbon tetrachloride only has LDF. Now, if you read the video description from 7.3, or if you just think about it logically, you can think of it this way. Things that have stronger intermolecular forces overall will have a lower vapor pressure, because for higher IMFs, it is harder for the liquid to turn into gas, because the IMFs are keeping the molecules together and tightly packed. Now, if you have weak IMFs, then that means that you will have a higher vapor pressure, because for weak intermolecular forces, molecules are not held together as tightly, and because of that, they can vaporize or evaporate very easily. And because of this, higher vapor pressure corresponds to weak IMFs, while lower vapor pressures correspond to higher IMFs. Now, what's going on in this question? Well, let me erase the ink and let's redo this. So, it says that dichloromethane has a higher vapor pressure than carbon tetrachloride, which has a lower vapor pressure. Now we know that dichloromethane has dipole-dipole forces and LDF, while carbon tetrachloride only has LDF. But according to our explanation, for a lower vapor pressure to happen, it must have stronger intermolecular forces, so this must be stronger. And since the vapor pressure is higher here, that means that dichloromethane must have weaker intermolecular forces. Now, at first you're like, wait a second, but dichloromethane has DDF and LDF, while CCl4 has only LDF. So how can this substance have weaker intermolecular forces? Well, the thing is that for high molar masses, sometimes the LDF can be so high that it trumps both of these IMFs. So in this explanation, you could say that the London dispersion forces in carbon tetrachloride is stronger than the combination of the dipole-dipole forces and the London dispersion forces of the dichloromethane, and because of that, dichloromethane will have the higher vapor pressure, while carbon tetrachloride will have the lower vapor pressure. So now let's take a look at E. They give us the complete Lewis electron dot diagram for methanol or formaldehyde in the box below. Molecules of methanol can form H bonds with water. In the box below, draw a water molecule in a correct orientation to illustrate a H bond between a molecule of water and the molecule of methanol. use a dashed line to represent the hydrogen bond. So if you remember, a hydrogen bond is a bond formed between the lone pair of F, O, or N. So let me draw a lone pair there. And a hydrogen bond forms between any of these three atoms as long as they have a lone pair with an H that is connected to an F, O, or N. Now these can go in any order, but as long as you have a lone pair attached to an F, O, or N, and a H that is attached to an F or N, you are good. So, in this case, I think the H's will be attracted to the lone pair on the O, and this will happen. So the H's might do something like this, and the H's will point towards the O with the lone pair, and the hydrogen bond will form right there. So that would be the answer for this question. And now let's take a look at the answers. So feel free to pause the video whenever you need to check over these answers, because these answers are the answers you are expected to be writing. And for example, these are all incomplete sentences and they don't use abbreviations. For example, they choose to spell out London dispersion forces instead of just writing LDFs. So let me just go through the rest of the slides, and feel free to pause the video whenever you need to. And these are the answers. And that's all for this video. Have a wonderful day, everybody.